Good morning, students. We are going to see today the case study for design of experiments. This I have taken from my PhD work. The title of my PhD work is Studies on Extraction and Microencapsulation of Morinda citrifolia fruit extract using spray drying. Because this fruit is available mostly in Southeast Asian countries, it has a high antioxidant potential. So, to extract these bioactive components by means of supercritical fluid extraction and the hot water extraction bath, after it has been extracted, it has been subjected to spray drying technique to obtain in powder form. Once this powder has been obtained, then we have tested the characteristics of this powder and tried to find the optimized process condition. So, how I have applied in the design of experiments in my PhD work, I would like to discuss. Regarding my PhD work, this is a fruit which has been usually having a high antioxidant value, which is commonly available in Southeast Asian countries, which has been peeled off and then cut down into minute small pieces. Then I subject to the sun drying. Later, some of the particles actually at the evening when I dry it, it becomes the fungal formation occurs. Then I understood sun drying is not a better option when compared to the oven drying. So later I subject to the oven drying and then the dried sample can be seen over here. Then later by pulverizer, I just dried the particles subject to the hot water bath extraction by using the particular solvent methanol, ethanol, and then you could able to see the lab experimentation extracted sample. Lab pic is there. Okay, I mean the conical flask along with the extracted sample is over there. This extracted sample has been subjected to spray drying and I have obtained the powder. So why I am trying to say this conceptualization is that is how to produce a bioactive component which is having a high antioxidant value. During this process, what are the variables which we have been subjected to, and what is the dependent variable, what is the independent variable in doing the design of experiments ultimately. So before getting into the thing, what I did is that okay, I just would like to show my methodology. The fruit has been peeled off, and then we have seen in the last slide, right? So make how I just make it into powder. So what are the techniques which I have studied? Encapsulation efficiency, particle size, moisture content, DPPH and TPC is there. TF. DPPH is a diphenyl picyl hydrazine, which will quantify the antioxidant activity, and the total phenolic content, total flavonoid content, which also talks about the antioxidant potential. Scanning electron microscope, surface morphology, atomic absorption spectroscopy, and FTIR, the functional group determination, Fourier transform infrared spectroscopy. During this process, I just add ethyl acetate by hot water extraction bath, and also I just subjected to supercritical fluid extraction by adding the methanol as solvent, and then the fruit extract, and then compare the hot water extract subject to the spray drying and the extract which has been obtained from supercritical fluid extraction subject to the spray drying, and then test the analysis. So here during the spray drying process, I have added two additives. One is maltodextrin and cake carrageenan. These additives will act as an encapsulated agent, so the bioactive component will be encapsulated inside the central core, and outside you will have a maltodextrin or cake carrageenan. Okay, so this is a spray drying technique. So you know already what is spray dryer. So the objective of this spray dryer is to convert the liquid extract into powder form, because the shelf life will be more easy to transport and so on and so forth. You have a high pressure atomization is there, which will convert the particles into liquid into powder form. Okay, and the evaporation may take place here, and you have a cyclone separator where it will separate the particles collected as well as the hot air. Okay, so I don't want to get into this part. This is how the spray dryer works. So the objective of getting into the spray dryer is two things. One is shelf life of the powder will be longer, easy to transport rather than having a liquid extract. Okay, so this is the advantage. Then we can make it into powder form. Once you make it into powder form, then it will be easy for you to go for a capsulation in as a capsule. Okay, so yeah, that means in table form. So this is my overall view of my project. So what I did in terms of design of experiments. So I am M core by M1, that is 1:1. So the core material and wall material. Wall material here I have taken as a cake original. The core material is a the extract. The temperature I just vary from 900 to 140 degrees Celsius, because during the design of experiments, okay, the temperature should not be very high. When you have very high temperature, there is a chances that bioactive component get vaporized. So we need to maintain a minimum temperature and an optimized temperature. So below which, even if the temperature has been very lower, that will not form a particles. I mean, the particles could not be formed. Okay. So we have maintained a minimum of 90 temperature, maximum of 140 degrees Celsius. So what are the parameters? That is a dependent variable is encapsulation yield, and encapsulation, once you obtain the powder, okay, then the testing analysis are mean particle size, diameter, moisture content. Okay, these are the testing parameters. Okay, sorry, these are the characteristic of a dependent variable, mean particle size, diameter, and moisture content. So this also supposed to be, moisture content is supposed to be low, and the particle size is supposed to be very small when compared to the larger particle size. So we are preferring the nanoparticle, or at least even microparticles. We have obtained microparticle size, that is 2.27 micrometer. We have obtained at 1:2 90 degrees Celsius for cake original, which is found to be an optimized point. And coming to the M core and the M core temperature. So for this temperature, the response, I mean the particles which we have obtained by spray dryer will have a DPPH scavenging activity. Okay, this value. So this results also, we want to optimize the response, that is a DPPH scavenging activity, total flavonoid content, and total phenolic content, and so on and so forth. So in that, which one will give supposed to be higher? I mean, the DPP is supposed to be higher, TPC is supposed to be higher, and total flavonoid is supposed to be higher. When compared to all this, the ranking is supposed to be given. Okay, because the DPPH value is more effective in terms of antioxidant activity. So even though the TPC and TFC also contribute to the antioxidant activity, when compared to DPPH, that will give you a better correlation to the antioxidant activity. So we will give you more weightage for the DPPH when compared to TPC and TF, total flavonoid. So in that case, so we have obtained the M core by M mol. This is a independent variable which will change. We get a powder. The powder is supposed to be a particle size supposed to be lower, moisture content is supposed to be lower, and encapsulation yield is supposed to be higher. Okay, this powder has been subjected to DPPH, TPC, and TF. That values has been also taken. So when you see here, when you for maltodextrin, the temperature is 1:2 at 90 degrees Celsius, 2.27.64 yield, percentage of yield has been obtained. It's very small yield, because the yield is not 80%. Encapsulation is normal actually in a spray dryer. Okay, so main particle size is found to be 4.82 for maltodextrin at that particular temperature. So the particle size is supposed to be lower. Cake original will give you better results, but maltodextrin is a little higher. But encapsulation yield for cake original is higher. So the cake original is better than maltodextrin for this case. Okay, so like that we found. So just try to understand the thing. So I am not projecting my results is a better results or something. So what I am trying to say, this is how we need to do the design of experiments. So for any experimental work, we need to adapt the nonlinear relation equations. For that, in order to find the process optimization, we need to use the design of experiments. Okay, and coming to the maltodextrin 4.82. Okay, so this is for DPPH, TPC, and total flavonoid for maltodextrin. And the design of experiments, once you see here the DPPH activity and total flavonoid content correlation. So when the total flavonoid content and DPPH having a correlation of R square 0.6, I mean for the data is 0.69 R square root mean square value. So we could able to find what you call the correlation design by using the design of experiments. Experimental design. So as I told you, three factor, three levels. So what does it mean by three levels? The three levels are, you see here, minimum, maximum, and low level. So here we have changed the two variables, two factorial method. One is m core by m wall. Okay, that is 1 is to 1 or 1 is to 2 we have taken. Temperature 90 to 140 I told you. So the maximum value is 140 degree, minimum value is 90. So the average value has been taken as 150. So difference is 50 divided by 3 50 divided by 3 is how much? So that range, particularly 25 range, sorry, 50, yeah, divided by 2, 50 range. So 90 plus 25 has been added. So the average value is 115. Here the m core by m wall is 1 and 0.25 has been taken. Okay. So this difference is 0.75. So the average value has been taken as 0.625. Average parameter has been taken as 0.2625. Okay, so the correlation, that means the minimum value has been taken as -1, maximum is +1, and medium level has been taken as 0. This is a coded value. And coming to here, we could be able to see the factors m core by m watt. The coded value has been given -1, 0, or 1, and the actual value and predicted value. So the actual value, by using the design of experiments, we will get a non-linear equation. For me, I got a quadratic equation between the variables, two factors, and we, with that equation, we have used the predicted value and we have calculated, and by doing the experiment we have calculated how much is the moisture content, dpph, tpc, tf, particle size, as well as what do you call particle size, as well as the another parameter which we have tested is a moisture content, right? Okay, so when you see here the actual value and predicted value, so we need to try to draw a graph and try to find whether the difference is very limited, is not much deviation, is positively correlated or negatively correlated, or exactly matching with the results. If it is exactly matching with the results, well and good. When you see here the statistical, by using the design of experiments, we have arrived out the variables, the effect of variables. So A is the temperature, B is the m core by m wall. So interaction between the variables A and B, the standard error, the confidence of interval 95% has been calculated, and whether what is the r square value, what is the adjusted r square, root mean square value and adjusted r square value. With that values, we just try to find this correlation is this is suitable or not. Okay, so what are the effects, whether the interaction is there or not? Interaction is a quadratic model. We got a square and b square. So in the last video I've shown x1, x2, x3 three factor design. This is only two factor design, two factorial. So you have a x square quadratic equation and the interaction between the variables x1 and x2, like that, right? In the similar way, here I just name it as, instead of x, I just name it as a and b. A and b talks about the interaction, a square is a quadratic effect. Okay, so by using this equation, so in the last video we saw the coefficient in beta, beta naught, beta 1, 2 and things like that. So you could be able to see the moisture content, how m core by m wall is correlated, the temperature B, how it has been correlated to the moisture content, what is the interaction factor A and B, along with that. So this equation which we have obtained by the RSO. So this is from the experimental value, is a empirical formula. No, is a what do you call, sorry, is a non-empirical formula, and we have obtained this equation. And coming to here, the response surface, moisture content and dppH activity in terms of three dimension. So the x, y and z values. So when you see here the dppH activity in the y-axis, when I change the variable between temperature and m core and m wall, what is the effect on dppH for moisture content, as well as moisture content and dppH has been shown over here. So it will give a flag. So flag means optimized point. At what point the maximum dppH has been obtained? At what point the moisture content maximum, lowest moisture content has been obtained? Okay, so moisture content is supposed to be lowest and the dppH activity is supposed to be highest. And coming to the cake original with the total flavonoid content and total phenolic content, again m core by m wall temperature. This is a sulfur three-dimensional plot. We used to call it sulfur plot. Okay, So in that plot, we by seeing the plot, we could able to identify at what correlation, at what optimized point the TPC and the TF is high maximum, that can be determined. And this is isoplate plot, how it looks like. Just look into the things. I don't want to get deeper into this part. Hope you understood how to carry out these experiments regarding. I mean, if you have for your case, for your final year project, how to implement the design of experiments for your case. Okay, so here if you see here, x1 is a temperature and x2 is a moisture content, is a two-dimensional plot. So you could be able to see the red indicates the higher moisture content, the blue indicates the lower moisture content. Actually, we want a lower moisture content. So the lower moisture content, so where the parameters comes into picture. Okay, so that you should know. And similarly here the DPPH activity higher indicates red color and blue color indicates is lower. When we want a temperature, we want a DPPH are supposed to be maximum. So this region there is a where the points are lying. Okay, that means the temperature and the M core and M1. So in that particular region, the optimized point has been identified. So similarly for isoplate for cake origin in terms of total phenolic content and the total flavonoid content. Here also the red indicates the highest point and the blue indicates the lowest point. Okay, similarly goes for the total phenolic content as well. Okay, so when you see here the predicted versus actual value by using the quadratic equation, the non-linear equation which we have obtained by statistical tool, that's what which has been inside the analysis design of experiments. Okay, so it will tell you that equation by using that equation without doing the experiment we can calculate the predicted value for any range, any range. Okay, but the actual value whether is very close to the predicted value, that is very important. Then means that our equation is valid. So when you see here for moisture content 11.49, here is 11.10, that is very closer value. Similarly for moisture content at 1:2 at 90 degrees Celsius, which is found to be very close, next close to the optimum point. Optimum point is found to be 1:2 at 95 degrees Celsius. So that is also 13.75 the moisture content, but when you bring it to 95 degree from for 1:2 ratio, you will get 11.49. So when I say, I already told you moisture content of the material is supposed to be lower. Why? Because the thickness problem. So when you have the powder which has been obtained with lower moisture content, so it will not go for a rancidity effect. Rancidity is a oxidation because of the atmospheric air which has been present in the atmospheric air when it has been subjected to open place, the material which will go for a oxidation in nature. That's why the people having a good packing, they will not allow the water air to get inside. So when you have the neglect the moisture content, obviously the shelf life period of the food material will be larger, or not only the food material, even the pharmaceutical products will be quite long. So if you see the tablets, some of the tablets they mentioned don't keep it in the refrigerator. Some medicines like tonic and all, they say just keep it at 4 degrees Celsius. Okay, so the purpose is in order to avoid the moisture content. Okay, so some samples are supposed to be kept at 4 degrees, some samples are supposed to be kept at the room temperature. So there's a reason for it. Hope you understood what I'm trying to say. So the moisture content for the powder, the spray dried powder is supposed to be lower because which we are being subjected to make it into a pharmaceutical what do you call a process, especially make it into a powder into a tablet form where we will have a high pressure compacting device which need to be used in order to make it into a powder to what you call tablet form. So the DPPH activity is supposed to be higher. When you see here at 1:2 at 90 degrees higher, but however we have just taken 1:2 at 95 degree as an optimal point. When you see comparison, why the DPPH activity is supposed to be high, but there is no significant effect. When you see when compared to moisture content, DPPH activity is also equivalently important, but there is no much difference between the values 24 and 90. Okay, whereas the TPC here 21 and 26, the optimum point is found to be 21. So 28 and 25 again 1:2 90 degrees giving an optimum condition. But yeah, so you see here DPPH, TPC and TF has been found to be higher, whereas the moisture content at 95 degrees Celsius is found to be lower. Okay, so again we need to have an interaction between which one is more important, moisture content or the other factors. Okay, then we will give a weightage, 4 or 5 rankings supposed to be given for each what do you call response variables. So the response variables supposed to be giving a rank. Accordingly, the system will find out which one is the optimized point. Hope you understood what I'm trying to say. So cake original and maltodextrin has been found as used as additives, and we have been compared their values. So here you see here cake original 1 is to 2 and 90 degrees Celsius at optimum condition, and maltodextrin in optimum, and maltodextrin at 1 is to 2 at 90 degrees Celsius. So the predicted value and actual value has been compared. So how much is the deviation? Okay, so you could be able to identify this from this. So if it is positively correlated, the predicted value is more than the actual value, that is possibly more correlated, that is more correlated, I mean a higher value. Is less correlated means is supposed to be at the bottom. If it is exactly matching on the center line, that means is exactly matching the correlation. Okay, so in this way, we need to conduct the experiments and then try to do the design of experiments and try to obtain the optimized point. Hope you will understand, I think, what I told regarding the essence of my PhD work, where I implemented the supercritical, where I implemented the design of experiments, even not only for hot water extraction bath, even for supercritical fluid extraction as well. So we can also compare between the different types of additives and try to find which one will give a better, or different types of extraction technique, and try to find it out which one will give you a better results by using a design of experiments. Okay, so the factors which we are going to vary here for my case is the temperature and M core and M watt. The other factors like if you want to compare between the supercritical fluid, and there is no point of comparing the supercritical and hot water extraction, which I didn't do, is that there is a reason for that, because the supercritical as well as what do you call hot water extraction, we are not supposed to compare, because this the next one, the later one, that is a supercritical fluid, is a energy intensive process. Okay, we need to bring the condition to a higher temperature and lower temperature and higher pressure. So in that case, we could not able to compare, because the energy spent on the process is more. Obviously, the efficiency also will be more. It will diffuse into the solid particles and then try to take out the bioactive material. Okay, so you should understand the unit operation and unit processes first before doing the design of experiments, and you need to, whichever is better, we need to take that one and then justify that one. After justifying the thing, when you try to do the experiment, what are the factors you would like to vary? Okay, and then what are the parameters, what are the responses you are looking for, how you are giving a weightage for that responses. Okay, that all is very important in the thing. And then how you are going to fix the this is my design of experiment methodology, whether you want to go for a two factorial method or box method, central composite method, or de-optimal design method, and so on and so forth. So we should have a very good knowledge on statistics as well as computational techniques. Okay, and then how this design of experiments have been carried out, and also you should have a better knowledge on the technical perspective of chemical engineering, like unit operation and unit processes. This all together will help you to get a optimized point. Okay, without this particular whatever I said is without a lagging of any of the things, okay, there's no point of going to that much extent of doing the experiment and then try to find the optimized point. So for process optimization is not easy. Okay, it's all coming together with all the strong knowledge on the subject. Okay, with this note, I just would like to conclude my case study. Hopefully, you will understand better. I think if you want any further doubt or anything, I am very well. We can discuss during the face-to-face section. We usually have every Wednesday of evening we have a class actually, face-to-face section. So we almost completed. I believe that is 8 or 9 classes is already over for us. So the remaining few classes only we have face-to-face section. Okay, so hopefully during that this face-to-face section, if you have any doubt, just come out with the as a flipped classroom, because this is a blended learning course. So just come out with your thing, okay, and then just message me before you come, or if you have any doubt or something, so that I can very well can prepare also. Or else if I am not aware of anything, because this subject is very new actually, because machine learning in the chemical engineers is not a new course. Actually, it has been booming up this particular decade. I mean, after 2020. So many people have, for the last 1 or 1.5 years only, the people have been talking about machine learning application in chemical engineering. So with this note, I just would like to conclude today's section. If you have any doubt, please come and knock me. I will I feel free. Please feel free to contact me. Okay, I will. I'm ready to serve you at my from as a lecturer. Okay, so thanks for your time. Keep in touch. So the second unit is getting over. There is a one subdivision which I need to take actually as a chemometric models in a unit one. That also I would like to cover in the next video. Okay, so please watch the video and try to understand. I am not going to post any of the MCQ questions for this particular case study because this is a out of the syllabus of unit 2. But however, I just would like to cover this content. What is my experience on design of experiments? How I carried out the design of experiments during my PhD work. Okay, so thanks for your time. Keep in touch. Thank you.